Welcome to qnawire.
So as the basketball rolls through the rough surface, the basketball gains some rotational kinetic energy as well as some translational kinetic energy. But as it moves up uh, the smooth slope, its rotational kinetic energy does not change since there is no friction. So first, since we are considering the basketball as a hollow sphere, we can assume its moment of inertia as ICM equals 2/3 mr squared, where ICM is the moment of inertia of the basketball. Now, when the basketball rolls without slipping, we also use this condition where the translational velocity is equal to r times the angular speed. Now, in our problem, we will be using conservation of energy here. So we can set this base as, or the valley as, y equals 0. So at this point y will be h naught, and let's say if the ball goes up to this height, then let's call this h. Right. So this is a two-step problem. First we'll be comparing the comparing the energies at this point and the valley. Then we'll do the same thing with the valley and height h. So first we'll be dealing with this part, then we'll do the other one. So in the first part, uh, if we say that k1 and um, k1 and u1 are the potential kinetic and potential energy respectively at point 1. So let's call this as point 1. So we just call it number 1. Then let's call this one point 2. Then at point 1, the sum of potential and kinetic energy should be equal to the sum of potential and kinetic energy at point 2. Now, few things that we need to notice here is at point 2, y is 0. So that's why the potential energy at this point will be 0. And at point 1, since the ball starts at rest, so kinetic energy will be 0. And the reason for that is because there's no initial velocity. But y1 is h naught, or the height that the basketball was initially. So we can easily see that u1 must be equal to k2. So u1 is mg h naught, and k2 has a translational part and a rotational part. So for translational part, we'll just call it half mvcm squared, and for the rotational part, it's half of moment of inertia times omega squared. Also, since we used I equals 2/3 mr squared, we can evaluate this part over here. So we substituted this quantity right here, and for omega, since it's rolling without slipping, so omega becomes vcm over r. So we put that over here. So using these two conditions, um, half of ICM omega squared becomes half of m VCM squared. Sorry, 1/3 of m VCM squared. So this quantity right here is 1/3 m VCM squared. So if we add this with the translational term, we see that mg h naught is 5/6 m VCM squared. From here, we can get VCM squared as 6gh naught by 5. Now we stop here for the first part, and we'll understand why we stopped here when we go to second part, where we have to find the height h. So in the second part, the rotational kinetic energy stays constant as it rolls on the frictional surface. So uh, on the valley there's only kinetic energy, so we have the rotational part and we have the translational part. But since the rotational part stays constant, then at the smooth surface, when the ball reaches height h, we'll have a potential energy plus we'll have a rotational kinetic energy, and this will be unchanged. So if the rotational part remains unchanged, so we can get rid of this because we have the rotational part appearing on both sides, so we can get rid of that. So from there we can see that height is equal to v squared cm over 2g. Now we can borrow this expression from the previous part and substitute back here. And if we do so, we'll see that h is in terms of h naught, and also this is less than 1, so that means the final height h is lesser than the initial height. So that means some energy, some amount of potential energy has been converted. Now we can easily say that since it was a rough surface, so that potential energy has been converted to rotational kinetic energy, and that's why there is less potential energy at the second height. So that answers part B, where it says why doesn't the ball return to height h naught. So potential energy gets some amount of potential energy gets converted to rotational kinetic energy. And that's why there is less potential energy in the second height. This is the reason we have less potential energy at the second height. Second height h. Thank you.